Let's break down every type of integral from high school calculus to quantum physics. First, the definite integral. This is used to find the exact area under a curve between 2 points, A and B. The notation looks like this. The elongated S is the integral sign. A and B are your limits. F of x is the height of the function, and dx represents a tiny infinitesimal width. Where is it used? Everywhere, from calculating distance traveled given speed to finding the center of mass of an object. Next, the indefinite integral. This is the reverse process of differentiation. It finds the antiderivative. Here, there are no limits a and b. Where is it used? It's used to find general formulas. For example, if you know the acceleration of a car, you integrate to get the velocity formula. Keep in mind, you must always add plus c, the constant of integration, because the derivative of a constant is 0, and we don't know what that original constant was. The improper integral. This happens when you get too ambitious. Either one of your limits is infinity, or the function breaks, has a discontinuity inside your range. Where is it used? Probability theory, like the bell curve, and calculating escape velocities in astrophysics. Keep in mind, you cannot just plug in infinity. You must use a limit. Replace infinity with t, integrate, and then take the limit as t goes to infinity. Sometimes the answer is a number, converges. Sometimes it explodes, diverges. Multiple integrals, double and triple. Instead of area under a curve, we're finding volume under a surface. The notation uses 2 integral signs for double and 3 for triple. Where is it used? Finding the volume of weird 3D shapes, or calculating the total mass of an object with varying density. Keep in mind, the order of integration matters. dx dy versus dy dx. If you switch the order, you must change your limits. The line integral. Here, we don't integrate along a straight x-axis. We integrate along a curvy path denoted as c. In the equation, we often use the dot product of a vector field f and a tiny step along the path dr. Where is it used? Physics, specifically calculating the work done by a force field, like gravity or magnetism, moving an object along a specific path. Keep in mind, the direction matters. The surface integral. This is the 3D version of a line integral. We integrate a function over a curved surface S. The key part of the equation is n, the normal vector, which points perpendicular to the surface. Where is it used? Fluid dynamics and electromagnetism. It calculates flux, how much stuff, water, electric field, flows through a surface. Contour integral. This is integration in the complex plane. The variable isn't x, it's z, a complex number. Where is it used? Electrical engineering, signal processing, and quantum mechanics. It uses the residue theorem to solve integrals that are impossible with regular calculus. The path integral. This is specific to quantum mechanics. It calculates the probability of a particle moving from A to B. The equation involves summing over every possible path the particle could take, weighted by something called the action, S. Where is it used? Quantum field theory. It explains why light bends and how subatomic particles interact. Keep in mind, this is not a standard Riemann integral. It is a functional integral, meaning you're integrating over a space of functions, not just numbers.